Now, the methodology of this PBE can be kind of summarized in 4 steps. Initially is the intensity measure that, okay, the earthquake strikes, what are the earthquake measures? Then is the engineering demand parameter, EDP, which, okay, if I apply that earthquake, that possible earthquake in my location to my building, what will be the response of my structure? Anyhow, we said that the behavior of the building is not based on the earthquake shaking, it's based on how much my building starts dancing and how much it will start moving. Based on that, I can fully understand what is the performance of my building. So I can then define some damage measures and I say, okay, if my building is 10 centimeters away, it's slight damage. If it's 20 centimeters away, moving is extensive damage. And if I reach to 30 to 40 centimeters away, that is collapse, that is problematic. So according to the performance of my building, I can define some damage measures. And now, having the slight damage, extensive damage, collapse, similar to the slide that we just saw, you can start estimating the casualties, you can start estimating the financial losses and downtime for your stakeholder and the building owner. And then if it's not good enough, then you can improve the building design to get a better performance under different shakings. So let's look at these 4 steps in more details. The first one, as we indicated, the intensity measure. So instead of using the simplified elastic response spectrum of the code and then using the Q factor for the ductility, we say no, we will trust and we will look at the probabilistic seismic hazard analysis of the location. And nowadays more and more of these studies are coming out for different locations of the world, so we can fully understand how the, let's say, the hazard of my location is. So according to that, I can estimate what intensity I should apply to my building at different times. Conditional mean spectrum is one of those, and uniformly hazard spectrum as well is one of those that in next session we will talk about these in more details. The coming sessions, each of them will be allocated and dedicated to each of these components of PBE in much more detail. And then having those hazards, we can get some intensities out of them. For example, peak ground acceleration, peak ground velocity, peak ground displacement, spectral acceleration at T1, spectral displacement at T1, Arios intensities, the newer intensities, and all of these were based on the reality. So the spectral shape, the conditional spectral, all of these, the frequency and duration of the earthquakes were considered in them. Now you might ask, what is aerial intensity? Imagine 2 earthquakes of Chichi and Hollister, different magnitudes, but they have the same peak ground acceleration. So if you just consider the peak ground acceleration, you're not considering the durations. Look at this. This was just, let's say, 21 seconds, while this earthquake was 80 seconds. For sure, when your building was shaking, although it was a high intensity, was for just 20 seconds, compared to the same shaking for 80 seconds, your performance would have been different. The area's intensity, as the formulation shows here as well, not only brings in the acceleration, but it brings in the time. It considers the time of the shaking. So it's a very good indication of how the shaking is from your ground. Now, the next step, engineering demand parameter. So I had the intensity, I know how to shake my building and how much to shake it. I know what earthquakes to select, and we will see how to select those earthquakes, which can be a good representative of your area. Now I want to see how my building is performing and dancing under those earthquakes. So the second generation allowed us to model our buildings in the most realistic way possible. So we had considered the nonlinearity, which not only exists in the material but also the nonlinearity in geometry of my buildings. Now different approaches exist and the detailing are different. We will have one session only dedicated on how the nonlinear analysis models work and how we do them. But in simple terms, if we look at different ways, for example, the nonlinear spring hinges, which OpenSys is one of the pioneers of it, you can have local damages properly modeled, like the steel beam. You can have finite length hinge zones, which again you can see it can replicate this steel column, which I think is based on the extensive axial forces. It's like proper local deformation, local buckling where it's connected to the foundation. Or the fiber sections. This is how Seismostruct mainly models the building, by dividing the sections into different segments and allocating some nonlinearity to just parts of it. This can clearly get the global buckling of a member, as you can see here. So there are different approaches. Some of them are concentrated plasticity. By plasticity we mean nonlinearity here. Some of them are distributed plasticity. You can just compare the simplest case, which plasticity is only concentrated at two ends of, let's say, this beam, and compare it to finite element softwares like ANSYS and OpenSys, which every single element that we have divided our section into has its own nonlinear behavior and geometric behavior, all nonlinear. By modeling our buildings, we could get the engineering demand parameters. Now these can be in terms of displacement, drift, rotation, whatever that we can relate it later on to the damage measures. Having our building modeled properly under nonlinear dynamic analysis, instead of having a simple monotonic pushover curve, we'll have a hysteresis curve. So tension, compression, push, pull, push, pull. So we'll see a full behavior of our building, and lots of studies have came up with component behaviors and defined materials. Like this one, modified Ibarra Medina Krawinkler model, which is based on 200 experimental data of RC beams. These models are implemented in our analysis softwares like OpenSys and Seismostruct. So whenever you define an RC beam, the software knows that this is the hysteresis behavior of that let's say component of your structure under any loading. Now this is moment rotation, so the software considers how you're shaking your building and it will follow such behavior. In that session, which is dedicated for nonlinear analysis, we will talk about these in more details, and the whole fact is that when you have the hysteresis behavior, you can consider the strength and stiffness degradation. Anyhow, material lose their strength. As you can see, this is the first cycle. The second cycle has less strength, has less stiffness. The third cycle, the same thing, less stiffness and less strength, and we carry on until full failure. Now, let's say that we had a successful modeling of our building. The outputs will be in different forms depending on how you want to analyze your data. For example, one of the most common ones is interstory drift ratio. That if you remember this guy, the drift of the second floor minus the drift of the first floor divided by the height was the interstory drift ratio. Now imagine that we have a 7-floor building of any material, and we have applied different intensities in terms of spectral displacement to it, from 4 inches, which is a very small, to a 24 inch. And then you can see each floor is performing differently, and we can see that the first floor in some cases is the worst case, while in some other cases the 5th floor is the worst case. So all of these can be concluding how the behavior of our building is. Or for example, the floor acceleration. We discussed this, that generally we work with displacement for structural components, and we work with acceleration for non-structural components. So remember this always, that the movement of the table, the movement of the chairs in the house usually is mainly measured with acceleration of that floor. Now, the deformation, the component forces, accelerations and velocities, all of these can be the output of our structural models. Now that we got those, let's say, responses from our structures, we can simply convert them to the stuff that you already know, fragility functions and vulnerability functions. Later on, again, a session will be just dedicated on how to translate those engineering demand parameters, get the help of intensity measures of the earthquake, combine these and come up with such curves which are probability versus an engineering demand parameter, which clearly indicates what is the performance of the building under different engineering demand parameters or different intensity measures. So instead of this can be IM as well, intensity measure, and then at different earthquake intensities you can simply say whether you have slight damage, moderate damage, or extensive damage. This is a good example of a fragility curve for a partition wall. You can see that under, let's say, these EDP of interstory drift, of very low interstory drifts, there is small cracks only, there's no problem, you just repaint it and everything will be fine. Probability of 50%, let's say. For a higher interstory drift, there is a higher chance that you will have more damage and you have to replace the gypsum boards. It's not just simply a repaint. For higher interstory drifts, for sure 50% chance that you have to replace the partition. So anyone, by looking at the fragility curve, can have a good understanding of what kind of damage to expect. Another term that we start from here, let's say we apply the intensity measure, the IM, to our building. Now the building will either collapse or there won't be any collapse. When there is no collapse, we will have different terms of damage: no damage, repairable, or demolition. How can I translate my performance of the building to any of these? Mainly through either let's say drift or displacement or acceleration. Any of these, which is the output of my model, can give me the chance to judge my building, whether it's no damage, whether it's repairable, is demolition, or collapse. Having the performance concluded, then the stakeholder can do the decisions. These decisions, first of all, is based on the risk of collapse of my building. So at very low intensities, if your building collapses, then there is a problem with your design. You have to go back and redesign your building to be safer. If there is a high chance of casualties, of injuries at lower intensities, again you have to go back to the papers and redesign your building. But if you design the building and the modeling showed that at higher intensities everything is safe, voila, you have done your job. Well done. Another important thing for stockholders, unfortunately, is the monetary or economic losses. The cost of replacement and repairs. You can clearly report all of these, as well as the duration of repair and reconstruction. Imagine a factory is stopped, then that is a problem, and you have to wait until your factory is repaired to start the production again. So meanwhile, you're not only spending money to repair, you're losing money because your factory is not operational and it does not produce any goods. That goes back to the downtime as well. The functionality of your residential, commercial, or industrial, which can get up to years or days, can be a big problem. But all of these can be concluded from a simple fragility curve and vulnerability curve. So simply, we just started again from intensity measure, we went all the way to decisive variables. So if we put all of these together, let's say the ground motion hazard estimation, which gives us the intensity measure, the response estimation from your structural modeling, nonlinear dynamic analysis, which gives us the engineering demand parameter EDP, you have the descriptions here as well. That EDP can be translated to damage estimation, which is the damage measure, whether you'll have slight damage, moderate damage, extensive damage, or collapse. All of those can be simply then concluded to the loss estimation, which is the decision variables. How much time will I lose in terms of downtime or in terms of repair? How much human life will I lose in terms of casualties and injury? And how much it will cost for me to replace my building or repair my building? Starting from the actual earthquake, looking at the actual response, understanding the consequences of that response, you can do the decisions. All of these formulations, IM, EDP, given the IM, DM, given the EDP, and DV, given the DM, can come to this formulation. This formulation, which I want you to memorize it, is the probabilistic description of a decision variable. But why it's a probabilistic description? Because our ground motion hazard estimation was probabilistic. Wasn't this a performance based on the probabilistic seismic hazard assessment? Was it this based on PSHA? Yes. So if my hazard is probabilistic, then every single one of those probabilities will result in a probable EDP, engineering demand parameter, in terms of drift or acceleration. Each of those probable engineering demand parameters will end up in a probable damage estimation. There's a probability of slight damage, there's a probability of moderate damage, there's a probability of extensive damage. Exactly what a fragility curve tells us. You see, there is 50% chance, this is a probability, that your wall will have slight damage, moderate damage, or extensive damage. Because everything is in probability, then your losses will be in terms of probability as well. So your client will see which losses are the highest probability, and if that is acceptable, perfect. If it's not acceptable, you as the engineer have to go back and do the design. And then uncertainties in the earthquake intensity, ground motion characteristics, structural response, physical damage, economic and human losses are all explicitly considered in every single one of these stages, as the PSHA does, as the structural modeling does, as well as the fragility curve derivation does, as well as the loss estimation. So you will report the uncertainties which every single one of these levels involves to your client, so they understand that, okay, none of these are deterministic, they're all probabilistic, and there are some uncertainties. So again, in simple terms, we started with a PSHA, and we kind of got what is the hazard of the location. From this, we got the intensities, we got the earthquakes, which are good representative of that area that we want, for example, our building or city be built. Out of those, we started analyzing our building according to what we have already designed. The analysis is based on nonlinear dynamic analysis, so we are considering the plasticity, permanent deformation, we are considering the nonlinear behavior of our structure, so as realistic as possible, instead of using behavior factor and design response spectrum. Now you see we are much more advanced. We have done a proper PSHA, so we don't need the response spectrum anymore. We have the structure, the actual structural response. We have modeled our building, so we don't need to guess the Q factor. Having the performance of my building under that intensity that I applied, I can have fragility curves, which are probability versus intensity, or EDPs. So the fragilities will give me what are the probability of slight damage, moderate damage, extensive, or collapse. And having those, that fragility curve can be simply translated to what we call vulnerability function or vulnerability curve, which simply tells us what are the losses. And this stage is where our clients are mainly interested in. One of the major concepts that you can see that properly is getting continuously referred to in this performance-based earthquake engineering is the concept of resilience. So in simple terms, resilience is the ability of the structure or the organization to go back to its operational, to its initial operational, full operation in the most controlled possible time. So the longer this time is, your less resilience. The shorter this time is, your business, your building is more resilience. So look at this. Loss of function, the more you get, the more functions you will lose. And recovery and rebuilding. So the more the time takes, you're less resilient. As well as you can bring in the cost losses as well. The more loss of function you have, definitely you will have more loss of money, as well as the repair cost will probably be higher as well. So remember what resilience is: the recovery and restoration of functionality. It's usually measured based on time. The more it takes your building to go back to its initial state, the less resilience your structure is. The less time it takes, the more resilience your structure is. So you always want to engineer your buildings in a way that they are more resilient, and not only they are safe after the earthquake, but the building and the organization is designed in a way that immediately you can go back to its operation. Now let's see what resilience means in other terms.
What is resilience? Social scientists, economists, architects, engineers, and others all have definitions of resilience that they use today. But what does resilience really mean in the context of the performance of our building stock after natural disasters? Consider the cities of Nashville and New Orleans, both of which were growing economically in the early 2000s, until in 2005, Hurricane Katrina hit New Orleans and caused an estimated $80 billion in property and economic losses. Over the ensuing decade, New Orleans continued to struggle to find its footing, whereas Nashville grew and thrived. If you think of Nashville as a proxy for what New Orleans might have been had it been more resilient, you can see that the city of New Orleans could have lost up to another $100 billion or more because it wasn't resilient. There are often a lot of public misconceptions about building codes. We often think of building performance along the dimensions of safety, damage or repair cost, and recovery time. It might be surprising to learn that code-based design is primarily focused on safety only and not the other two dimensions. Engineers and architects must use resilience-based design to get a holistic understanding of the performance of buildings across all three dimensions. Let's look at Christchurch, New Zealand, a once thriving city of 400,000 that in 2010 and 2011 was struck by two very powerful earthquakes. The good news is, of the thousands of buildings in the central business district, only two collapsed. However, economic losses were on the order of $25 billion, and over 70% of the buildings in the downtown district had to be demolished because they were so heavily damaged. So did performance meet expectations? Well, it depends who you ask. From a code perspective, only two buildings collapsing out of several thousands is certainly a measure of success. But if you talk to the people that lived and worked in Christchurch, the performance certainly didn't meet expectations. The U.S. Resiliency Council was founded in 2011 as a 501c3 nonprofit organization. Our vision is a world in which building performance and natural hazards is understood, and our mission is to establish and implement rating systems that describe the performance of buildings during earthquakes and other natural hazards, so that communities and companies can build a more resilient future in a way that everyone can understand. Building owners and tenants, communities and companies can use U.S. Resiliency Council rating systems to describe the performance of the buildings in which they live and work across the dimensions of safety, damage, and recovery. Buildings that meet or exceed building code expectations can be awarded a placard for public display. When cities use the U.S. Resiliency Council to rate their buildings, they develop a better understanding of their strengths and weaknesses and can use that information for long-term planning to make their communities more resilient in the future. Architects and engineers are using the U.S. Resiliency Council rating system to design new buildings to achieve higher levels of performance and resilience. You might be surprised to learn that achieving a gold or platinum USRC rating typically only adds between 1 and 10% of the overall construction cost to a building. By using the U.S. Resiliency Council rating system, architects and engineers can bring value to cities and companies by developing long-term strategies to improve disaster recovery and resilience.
So as you see, the performance-based earthquake engineering is allowing the measurement of resilience of the structure, and these guys are giving placards to buildings based on how resilient they are, not only in terms of the structure, but it can be applied to the organization and the business as well. So there are different placards that they give with different definitions. If you're interested, please have a look. A very similar approach for earthquake resilience is what Arup does for organizations as well. And not only they consider the earthquake resistance of the structure, they also look on how resilient the organization is and how the business is and how much it takes it to go back to its normal and recover. It's called the Red Eye rating system, or the READY rating system. It's developed by Arup, and they have some publications regarding this.